This conference will now be recorded.
Very good evening, students. As you have decided in the last class that we will learn in detail about capacitor and capacitance. So today we will start this chapter, this particular topic in electrostatics, and then we'll actually solve many numerical problems on this particular topic because it is very important topic and important for both JEE NEET exams. So we'll learn intricate physics behind the capacitor and capacitance, and we'll learn here how to calculate capacitance for various geometries. Okay, so first of all, what is the capacitance or capacitor and all, we'll just first learn, and then we'll go to the detailed learning. First of all, see, conductors, we have already learned that conductors, right? So conductors have free electrons, right? Actually, free electrons doesn't mean that they are freely available in the air, just like one electron here, one electron here, or one electron here in the air, it is just floating. It is not the case. Okay, free electron cannot be like this because they are very much reactive. They will be absorbed by some other molecules or atoms, so that free electron does not exist in the air or in empty space. Actually, what I am trying to say that you cannot hold, you cannot hold, you cannot hold an electron or a free electron, I can say a free electron or free charge, not only free electron, free charges also you can say. Free charges, we should say free charges. Free charges. Okay. So we cannot hold it, or we cannot just place as we want. Okay. We cannot, in fact, we cannot actually control, or what to say. I mean, free charges. First of all, it is not available in the air or empty space. They are there in the conductor. So what I'm trying to say is that the free electrons better to handle, like we cannot handle it. Since we cannot handle it, better to put in the conductor. Just put the charges, free charges, to the conductor. Okay, we cannot handle it, we cannot actually keep as we like. But one property these conductors have, that they can actually possess free electrons. That means they can hold it inside them. Okay, so if we want to store free charges, only way to put that free charge, put the charge onto the conductor. Okay, and that conductor actually will hold the charge. Okay, but these conductors also will have their limit. Conductors will have their limit. So we have learned what we have learned. Conductors can store. Conductors can store free charges or charges, electric charges, I can say electric charges electric charges. Okay, within them. So conductors can store electric charges within them, but they have like they have some limitations. Okay, some limitations. They have some limitations. Beyond that, they cannot store more charges. Okay, but see, these conductors could be used. This conductor can be used for storing the charges, but not the isolated conductor. We generally use a pair of conductors and a medium between that. Okay, that is called dielectric medium, or insulating medium inside. So two conducting plates, and in between there will be some dielectric material. So this combination will actually help you to store charges as you like. I mean to say, you can just choose the area of these plates. You can choose the medium between the plates. You can choose the gap between the plates. So by changing the geometry, changing the distance between them, changing or altering the medium in between, we can actually manipulate the capacity of this combination of the plates to store the charges. So capacity, so there are different capacities of different isolated conductors to store charges, but what we are talking about is capacitor, which is a device which can store more electric charges or potential energy compared to an isolated conductor. And see, this is one such like pair of parallel plates, conducting plates, isolated by a very small distance d, and they're identical plates, so area of cross section will be a, and medium in between, that is some dielectric medium. So this combination actually is called capacitor. This is the device. So this is the device which can be able to store more electric charges than an isolated conductor, just like this. Okay, so this is actually the definition of conductor, sorry, capacitor. So capacitor, the capacitor actually is denoted, you might have learned already, denoted by this. Okay, so in this case, one will be positively charged plate, another will be negatively charged plate. This is parallel plate capacitor, or anyway, the this is the circuit symbol of a capacitor. Okay, all right, now we'll see what is capacitance. Okay, what is capacitance? Capacitance of a capacitor. See, as I said, the conductor can store energies, or capacitors can store energy or charges. But every capacitor will have their own capacity or the maximum limit to store the energy or charges, electric charges. So that capacity is actually measured by the parameter called capacitance. Okay, that parameter is called capacitance, which measures the limitation or the capacity to store the charge. Okay, and see, if suppose I have a conductor, some arbitrary shaped conductor. Okay, I put some charge q to it, some positive charge q to it, and the charge will be distributed uniformly over the surface of this conductor. So this is a conductor. Okay, I'm just putting some charge Q onto it. So that's how it got a charge, and charge got uniformly distributed. All right. Now, due to this charge, there will be potential develop in this, and say the potential develop is this. Okay, potential developed in this conductor is V, and obviously this V will be directly proportional to Q. If you add more charge, then potential will be stronger. Okay, if you give less charges, then the strength of the potential will be less. That means, you know, the potential is directly proportional to the charge added to it. Okay, so in any case, whenever we get a proportionality relation, to get quantitative idea, we should get this relation in terms of equation. So I'll just write V is equal to Q, but always there will come a constant, proportionality constant, and that is here, suppose 1 over C. 1 over C. So 1 over C, this C, so this is proportionality constant here. So 1 over C is the proportionality constant. Little constant. Okay, 1 over C is the proportionality constant, and C is called capacitance of the conductor or the capacitor. All right, so see, then I have got some relation between charge, potential, and capacitance. So see, Q is equal to CV. This is one relation. Or if I want to find out C, then Q by V. So these relations are prominent now from here. Now, what is this capacitance we have learned? We learn yes. So this is what actually I have already done. So capacitance we have already for an isolated system. So capacitance is Q by V. C is equal to Q by V. We have already found out this. And see, what is the SI unit of this? SI unit of capacitance. See, if I write just absolute unit of this both charge and this potential, then we know this will be coulomb and this will be volt. So coulomb per volt, but it has got some new name that is called farad actually. Okay, capacitance is farad. So let me tell you, this farad is actually a very big unit. So that's why in practical use we don't use this farad unit, because this is a big unit like million has got its smaller version of units, etc. So farad will be a kilogram, gram, right? So similarly here farad has got like meter, kilometer, centimeter, decimeter, all those things. So similar to that, we use in practical life, will be using, so this is a very huge unit actually, farad. So we use microfarad. Okay, so farad is generally written as capital F, and smaller units are, see, we can write millifarad, but most usable unit is this microfarad. Okay, nanofarad also, picofarad also. So millifarad generally it is not used much, but micro, nano, and pico, these are These are actually usable unit in practice. So microfarad means how much? 10 to the power minus 6 farad, and this is 10 to the power minus 9 farad, and this is 10 to the power minus 12 farad. So these are units, usable units. Okay. So now how to calculate capacitance? See, how to calculate capacitance, we have known already the relation C is equal to Q by V. C is equal to Q by V. That means, if you want to find out capacitance of a conductor, then put some known charges Q onto it. Put some known charges on the conductor, onto the conductor. Put some known charges, suppose that is Q. Okay, known charges, suppose that is Q, and due to that, the potential developed we have to calculate. So once we know the charge and once we know the potential developed across this conductor, then it is easy to find out C is equal to Q by V. Okay, C is equal to Q by V. How do we do that? How do we calculate? We give this Q amount of charge, known charge, to the conductor, and then we find out the potential difference across the ends. Okay, or potential difference due to putting the charges. Once you get that, we take the ratio of charge to the potential to get the capacitance. Okay, now see here, I have got a spherical capacitor. Okay, I have got a spherical, I mean to say, okay, so we know C is equal to Q by V. This is the way, and this has got unit farad or microfarad. Farad is actually written like this. Microfarad is written like mu farad, and then nanofarad is written NF. Picofarad is written PF. P is small and F is caps. Okay, capital. In each case, these are the things. Okay. Now suppose I have got a spherical uh, capacitance of a spherical conductor. So this is a spherical conductor. Okay, first of all, suppose it did not have any, initially it was uncharged. Suppose there was no charge on it, so a known charge Q is put on it, and then the charge gets redistributed uniformly over the spherical surface. Now if we can calculate the potential Q, anyway we know here, if we can calculate the potential on the surface, so that we can find out like this, right? So K into Q by R square, sorry, R. So this is the potential, we know, right? So K also, let us write this, Q by 4 pi epsilon naught R, and epsilon naught is permittivity in free space, we know that. Okay, then see, if we want to calculate what is C, we know C is equal to Q by V. So from using this, how do we calculate for this spherical conductor? C is equal to Q by V. Okay, Q by V. Q by V means what in this case? So Q we know already, we had. Okay, so Q by V from here. See, from here Q by V is nothing but equal to 4 pi epsilon naught R. So this is the capacitance expression for the capacitance for any. Suppose there is a bubble, water bubble having charge, some charges. So this is a spherical in shape. So it will have 4 pi epsilon naught some R1. This will be the capacitance of the spherical one. Okay, so to calculate capacitance for a spherical conductor is very simple. Then 4 pi epsilon naught R. Now see, I'll just take up one example. Suppose the arc. Okay, you know the arc has got, okay, so just this side I'll erase. So arc has got radius, how much? 6.4 into 10 to the power 6, I guess 6 meter. So 10 to the power 6 meter. Okay, so this is the radius of the arc. Then can you calculate the capacitance? Calculate the capacitance of the arc surface. Okay, so this is the question. So what is this? See, C is equal to, what we know for a spherical capacitor, spherical conductor, 4 pi epsilon naught R. So see, 4 pi epsilon naught means 1 over 9 into 10 to the power 9, and this is, see, R is given in SI unit itself, 6. So this will give you the unit of farad. Okay, that means see here 6.4, or you can write 65 also. Sorry, 64 by 9, and this is 10 to the power 5, 10 to the power minus 9. Okay, this is then 64 by 9 into 10 to the power minus 4. See, if I just do this calculation, oh, I see. So here it is 1. So this is 10. 10 by 1. So this is 1 again. Okay. So 7, 1, 1. Okay. So look, this I get 7.11. This will be 7.11. Okay. I'm sorry. 7.11 into 10 to the power minus 4 farad. So I can just convert this into microfarad. 700. So this is this much farad. That means, you know, the earth has got 711 microfarad. This much microfarad capacitance. So now you can like you can understand, if the earth, such an earth has only 711 microfarad, then how big the unit of farad is. Okay, how big the unit farad. Farad unit is very like very large. Okay, now we'll just take one simple numerical example to understand how to calculate the capacitance. Okay, now see, this example says radius of a spherical conductor is given. See, radius of a spherical conductor is given 2 meter. This is kept in a dielectric medium of dielectric constant given like this. I think it is actually Newton per coulomb. Newton per coulomb. Find capacitance of the conductor and maximum charge that can be stored in the conductor. See, anyway, one thing is very clear. That is this is spherical conductor, so we no need to bother much. So we know capacitance for a spherical one will be C is equal to 4 pi epsilon naught r. So where r is, okay, r is given here 2 meter. Okay, so first option, let us finish first question. So this is so this is 2 meter. Okay, now this will be nearly equal to 2.2. Okay, 2.2 into 10 to the power minus 10. This is capacitance, that is farad. Okay, this one's farad. Now what is the maximum charge which can be stored on this conductor? See, if we put some charges in the conductor, it will be obviously developing electric field around it, and that electric field will be maximum only when the charge q is maximum for a point charge 4 pi epsilon naught. Okay, so electric field should be like this, and this maximum electric field must be equal to this constant. What is this constant? This is dielectric constant. Beyond that, the dielectric material will be ionized, and the capacitance of the capacitor will decrease. Okay, or the capacitor will not act as further capacitor. So we need to find out what is the capacitance of the conductor, that we have already found out. What is the maximum charge that it can store? So Q max will be E max into 4 pi epsilon naught So what is this Emax? Emax is actually here 10 to the power 6 Newton per coulomb divided by 4 pi epsilon naught, 4 pi. So this will be down anyway. So 9 into 10 to the power 9 into r square. R square is 4 again. Okay. So then we can actually do the calculation part nicely and can get the maximum charge. Okay, so this will be the value, maximum value. So this is coulomb. In coulomb it is now. Okay, so if you solve this, you will get the answer for this. Okay, now we'll go to learn one important topic in this capacitance and capacitor chapter, that is energy stored in charged capacitor. Charged capacitor. See, suppose I have initially two parallel plate capacitor, initially suppose there was no charges. Now if you connect a battery to charge this, initially some charge will be sitting here, initially, and also there will be some lack of negative charges or excess of some positive charges. So some charges, once you apply a battery or circuit, some charges will actually be there on the conductors. Now if you suppose these conductors, when they are fully charged, has capacitance q, capacitance q naught, and it develops potential difference as v naught. So I I think I should write this as caps v0 when they are actually fully charged. Okay. Now suppose in between a charge q, is transferred. It's transferred to the positive plate. Suppose this is positive plate, this is negative plate. Positive plate to the negative, from the negative plate. Okay. So that means, you know, q at some point, q here, q has been developed, plus q here, minus q, and suppose due to that potential is v. Okay. So the capacitance, or we can write that volt, this as q by c. Okay, this is the voltage developed across the conductors. Now say dq amount of charge, amount of positive charges are brought from, suppose this is A, this is B, from B to A. That means, you have to actually do certain work against the repulsion, because you are taking positive dq charge and putting it here, and here already positive charges are there, so it will be repelled by the charge existing on this conductor. So charges are brought from B to A. So work done against work done against repulsive force. Repulsive force. Work done against repulsive force will get stored as the energy or electrostatic energy in the conductor. Okay, energy, just I'm writing energy. Okay, so what is the work done, by the way, to bring, say I am writing here, there is already q plus q, here there is minus q, potential difference is V. Now one dq charge is been taken here and added. So work done will be V into dq, V into dq. V is q by c and this is dq. Okay, if you are charging it full, then 0 to V0. So this is dw. dw is equal to this. So this will be V0 is equal to q by c. In the dq integration with limit will be, this is half q naught square by c. Okay, this is actually, I'm sorry, this is a work done, and that actually gets work done means that gets stored as potential energy as well. Anyway, so we know the energy stored gets stored. Let us say this is W itself, or this difference is actually V. Okay, let us say this is V. So what is the energy stored? Better to write this as U. electrostatic energy stored. So Q naught square by 2C, this is the energy stored, total energy stored by the capacitor. Okay, so we can actually convert and write this equation in different ways. Q0 is equal to CV. So if we put this, we'll get U is equal to half CV, half CV square. Okay, so like that we can actually interconvert in many terms, like 2-3 terms. Again, we are not doing here. So I have remembered it like this, half CV square. Okay, this is electrostatic energy stored in the capacitor. All right, so we'll see how charges get redistributed when two charged capacitors are connected together. Since there are two capacitors C1 having C1 and Q1. C1 is the capacitance and Q1 is the charge. So this has got C2 and Q2 is the charge stored in it. Now, if we connect these capacitors in parallel, okay, if we connect these two, then what will be the common potential? What will be, like, see, I just mentioned only. So if I have two capacitors, like capacitors having two different capacitance, one is actually, see here, if the charged capacitors are connected via a wire, there will be redistribution of charge, and the situation here, like redistribution of charges here, can be explained with a very common example, that is here. See, suppose here there is a tank or a container of water, and which has two cylindrical mouth, say cylindrical container. One has, suppose, volume V1, another one V2. So where V2 is greater than, much greater than V1. Okay, so the volume or the capacity to hold the water is different for these two different cylindrical parts. Now initially, suppose they are filled with different level of water, and the valve which is connecting between them is tightened very firmly, and making this as waterproof, this valve. Now if we open this valve slowly, then what happens? The water, see, come down here and go through here, and it does not increase the height of the, sorry, it actually, see, when this liquid passes through this valve and go to the other, so obviously this level will increase. Okay, and when the flow of liquid will stop for this, that is the time when the height of the liquid, like top surface of the liquid, becomes equal. So in this case, if the level of the water becomes equal, then what happens? Flow of this charge, sorry, flow of this water stops. Okay, so in this case, we see the final height, final height, final height, that is same, becoming same or common for both of them. Similarly, if we just connect them together, this capacitor also, then what will happen? So when these two are connected together, then their potential will be the same. Their potential will become same, and that potential is called the common potential for the capacitor. So in case of capacitor, until and unless their final voltage, sorry, potential difference is becoming equal, or potential becomes equal, the charge transfer will happen, or redistribution of charge will keep on going. Okay, now see, I have here the real example. See this real example. Before the example, let me write few things over here. So suppose there are initially two charges Q1 and two conductors which are carrying charges Q1 and Q2 initially. Okay, so initially they are carrying charges Q1 and Q2, and each of them has radius like R1 and R2. They are not equal anyway. So after they are connected with the conducting wire, see their potential becomes equal, but the charge stored by them will be different. Okay, so now, so in this type of question, there will be problem to ask, like to find out problems to find out what is the common potential for these two charges. Okay, what is the common potential? So that kind of question will come. We have to find out the common potential. Okay, so how do we do that? See, we know these are spherical conductors, so we know Cu1. Suppose capacitance for this is C1, so this could be, and for this is C2. Actually, we can write C1 by C2 is equal to, or C2 by C1. Anything we can do. C1 by C2 is equal to R1 by R2. Okay, R1 by R2. Similarly, so what will be the total charge actually? See Q1 prime now, new charges. They got redistribution. That's why this one. So this is Q1 plus Q2 total charge. So Q1 plus Q. So this is actually, we have to write in terms of C1 and C2 also, and an R1 and R2 also. Actually, total, the common potential will be given total charge by, so total charge, or I'll write Q total. Okay, so common, I'll just go to the next page. So common potential will be equal to total charge by total capacitance. So the common potential will be total charge is Q1 plus Q2 divided by total capacitance C1 plus C2. Okay, this is the common potential. Okay. Then how to find out Q1 prime charge on new charge on the capacitor capacitor C1. So Q1 will be C1, capacitance anyway doesn't change, but this changes. Okay. So C1 into V is the common potential. So VC common. So C1 divided by C, this is C1 plus C2 into Q1 plus Q2. So this will be the new charge on the capacitor 1 or conductor 1, and new charge on the other one will be Q2 prime is equal to C2V common. So C2 by C1 plus C2. Okay, so this will be actually the new charges and the common potential. Okay, so this is common potential, this is common charge, sorry, new charge on C1, new charge on C2. So this is how we have to actually remember this formula at least. Then we'll solve this problem. See, we have one topic. I'm just writing the title, but this will show you in the next class that there will be loss of energy. Suppose I have capacitor C1 fully charged, another capacitor C2 fully charged, and then connect together. So there will be redistribution of charges according to the capacitance of the capacitors. Okay, so there will be loss of energy. There will be loss of energy for this combination. Okay, so this loss of energy will calculate in the next class. Today we'll just solve one numerical problem and stop. See, two isolated spherical conductors have ready. So suppose R1 is 5 centimeter and R2 is 10 centimeters. They have charge of, okay, so this has got charge Q1, 12 micro coulomb, minus 3 micro coulomb. Okay, so find the charge after they are connected by conducting wire, and also find out the common potential after distribution of charges. So how do we do that? We have to first of all calculate the capacitance. So capacitance will be, so C1 by C2 is equal to R1 by R2, as you have seen, and that is obviously equal to Q2 by Q1. Sorry, Q, yes. So C1 by C2 we have already found out. So this is nothing but Q1 prime, or Q1, yes, Q1 prime by Q2 prime. So that is equal to 5 by 10. Okay, so this is Q1 by Q2. So I can actually find out what is Q1 prime. So Q1 prime will be Q2 prime. So Q1 prime, if we calculate, actually, see, how do we know how to calculate Q prime? So Q1 prime calculation is C1 by C1 plus C2, C1 plus C2 into Q1 plus Q2. Okay, so this is the one. So C1 we know. C1 can we find out? Yes, from here we have already found out. Okay, we can find out C1. So Q1 is found to be 3 microcoulomb. And Q2 in that way, Q2 prime will be this is, I'm sorry, this is Q1. So this will be 3 microcoulomb. Two by 1 plus 2. This is 10 microcoulomb. Okay, this is how we can actually calculate. Okay, next is that potential, common potential. It should be Q1 plus Q2 divided by C1 plus C2. Q1 plus Q2 already we know how much it is. So Q1 plus Q2 we know 10 to the power minus 10, see 9 to the power minus. So this I can write 4 epsilon naught R1 plus R2. Okay. So if we put the values R1 and R2 and this value also, so we'll get 5.4 into 10 to the power 5 volt. Okay, so we'll stop it here for today. Next day we'll take up more problems on this particular topic, redistribution of charges. Okay, so thank you for your presence. Bye for today.